Hello, everyone. Okay, today we are going to solve some problems. During the previous week, we mostly focused on complexification and tensor products. Since this is a more abstract topic, I would encourage you to think more about that. Today we would continue to the next topic, but I think that would be quite useful if you spend more time on that, and we can discuss it again whenever you have a question. You can send it to me. I would expect the kind of proofs maybe you would see in future, they would use this kind of complexification and tensor products and category things which we talked about. These parts, they are useful in certain areas of pure math. But I don't think you would see those specific parts a lot in applications of linear algebra. Anyway, today we continue, since the kind of the main topic of your homework this time is kind of around determinant, kind of the central object in your homework is determinant. I'm going to review some basic things about that, and we would think about some questions about determinants. Okay, so let's start. Okay, great. So let's start from some very basic things. Let's review with some background. Remember, if you have an n by n matrix, so suppose we have some n by n matrix, say with real entries, we would say this matrix A is symmetric. If it is symmetric with respect to its diagonal, in another terms, its transpose is equal to itself. Recently, we talked more about diagonalization. An interesting theorem is that any such matrix A is diagonalizable. In other terms, there exists an invertible matrix P such that P inverse AP is a diagonal matrix. You might have seen the argument for this statement before, but I like to kind of review that. This is a form of argument which you would see in other cases too, not exactly about symmetric matrix to be diagonalizable. We see that in other forms of matrices have being diagonalizable, for example. So I'd like to review that more carefully one more time. So why is that the case? Just note that a matrix being diagonalizable, it means that, for example, if it's an n by n matrix, we can think about that matrix as a linear map from Rn to Rn. Right. And being diagonal means I can choose a basis for Rn. So I can choose a basis B, let's say E1 up to En, where A of each EI is some lambda I EI. So I can choose a basis for the space, for our vector space, such that that basis is actually a basis of eigenvectors for A. And in that case, the matrix A, if I change the basis and rewrite that operator in this new basis, B, which is equal to some P inverse AP for some P, it would be this diagonal matrix. right? Now, why is that true? Why is that true about symmetric matrices? So suppose A, so let's assume A is such a matrix, is an n by n real symmetric matrix. Before directly proving that statement, let's review a simple fact about such matrices. Suppose we take two distinct eigenvalues of A. Suppose lambda 1 and lambda 2 are two eigenvalues of A. Where they are not equal. So lambda 1 is not equal to lambda 2. There are two different eigenvalues. So each eigenvalue, well, by definition, has an eigenvector, right? Suppose the eigenvector corresponding to lambda 1 is v1. And the eigenvector corresponding to lambda 2 is v2. So it means A lambda 1, sorry, A v1 is equal to lambda 1 v1, and A v2 equals to lambda 2 v2, right? Now, one simple thing is that if we look at these two vectors v1 and v2, they end up to be normal to each other. In another terms, v1 inner product v2 is 0. They are normal to each other. So the eigenvectors corresponding to different eigenvalues, they will be normal to each other in this case. So why is that? It's a common trick, actually. It would be good if you think a few minutes about that, and then I would write down the reasoning why that would happen. So think about it maybe for 2 minutes, and then I would write the reason. Okay, let me write down the proof. So first, note that it is interesting to note that when we have two vectors u and v, the inner product, which we show it u inner product v, it can be written in two different ways. So u is a vector, like u. Did I use v1 and v2, I guess? Yeah, sorry. So let's use the same notation. Say v1 and v2, we have two vectors v1 and v2. If v1, the vector v1 is equal to, say, a1 up to an, and the vector v2 is equal to b1 up to bn, well, we know the inner product simply is the sum of ai bi, the standard inner product on Rn, right? There are two different ways to present the same quantity. Note that V1 can also be considered not only as a vector, but also as a matrix, because any vector is a matrix. Any vector is an n by 1 matrix, right? So I can think about the transpose of this matrix, and it would be 1 by n matrix. And now I can multiply this matrix by V2, right? Because this is, well, V2 is n by 1 matrix, and then V1 is an n1 by n matrix, and their multiplication as a matrix makes sense. Makes perfect sense. And it is the same number as the inner product of V1 and V2. This is also equal to V1 dot V2, V2 transpose. It's also equal to V1 inner product V2. Maybe I shouldn't use dot here. This is these two are matrix multiplication. and this here is inner product. Right. So having that in mind, yeah, that is correct. Sorry, we want 1 by 1 matrix, so I should multiply. You are right. We want 1 by 1 matrix, so I should multiply V2 transpose. You are perfectly right. If I multiply V2 transpose, it would be 1 by n, and then I can multiply it by 1. That is correct. And V1 transpose V2. Okay, here we go. So having these two in mind, having this kind of notation in mind, let's continue. Now we have this matrix A, which is symmetric and n by n, right? Let's consider this quantity. Let's consider V1 transpose, which would be an 1 by n matrix. Let's multiply that by n. That's an n by n matrix. And then let's multiply that by V2, which is n by 1 matrix. So it makes sense, right? We have 1 by n matrix, which is V1 transpose. You have A, which is n by n matrix. And then we have V2, which is n by 1 matrix. If we do this multiplication, the result would be a 1 by 1 matrix, which is just a number, right? A 1 by 1 matrix is just a number. So let's give it a name. Let's call this thing, I don't know, let's call this just B. So I would erase this A here too. Oh, the zoom on iPad has changed slightly. I'm not used to this new user interface. It's slightly different. Okay. So we have this number, right? Now let's compute. So it's a number. Maybe I shouldn't even show it with that. Let's call this number. Let's call this number X, because it's really a 1 by 1 matrix, which can be thought of as a number. Now let's see if we can compute that. What is a V2? Well, V2 was is a vector, eigenvector of A, so it would be V1 transpose times lambda 2 V2. Now lambda 2 is a real number. I can just write it as, I can just change its place with V1 transpose. I would get lambda 2 V1 transpose V2, right? That would be my value X. Now, as you know, this V1 transpose V2 is just the inner product of V1 and V2. Now, on the other hand, because X is a 1 by 1 matrix, its transpose is equal to itself. On a 1 by 1 matrix, the transpose does not do anything, right? But what is X transpose? Well, X transpose is the transpose of V1 transpose A V2. Now remember, there is a simple lemma that, so I would just write it here, simple lemma, AB transpose is equal to B transpose A transpose. Taking transpose of multiplication of some matrices changes the order of those matrices. So this would be V2 transpose, A transpose, V1 transpose transpose, but they cancel each other, so it's just V1. Now here, the crucial assumption about A would enter the argument. A is symmetric, therefore A transpose is equal to A. So this is equal to V transpose A V1. Now on the other hand, V1 is an eigenvector of A, so A V1 is just lambda 1 V1. And it's just a real number. We can that would commute with V2 transpose. And V2 transpose V1 is just the inner product of V2 and V1. And well, that's equal to inner product of V1 and V2, right? The inner product is commutative. So, sorry, it's lambda 1. So what does this tell us? Well, this quantity here, lambda 2 V1 V2 is equal to this quantity here, lambda 1 V1 and V2. But that is not possible because lambda 1 is not equal to lambda 2 unless V1 dot V2 is 0. So therefore, we have V1 dot V2 is equal to 0. So the eigenvectors are normal to each other. Also note that we used the fact that A is symmetric, and if A is not symmetric, that's definitely not true, because you can construct a matrix which is not symmetric, and it has, for example, say you can take look at R2. You can define a linear map from R2 to R2. Let's say this is V1 and this is V2. This is a basis for R2. I can choose this basis, right? And I can define the matrix A by saying it sends V1 to 2V1 and V2 to 3V2, right? Here I have two eigenvectors, which they are not normal to each other, but they have different eigenvalues. And there is no contradiction here. The point is that the map here, if I look at this basis, this map is not, or any other basis, this map is not, the matrix is not symmetric, right? So that assumption is crucial. Okay, so knowing that, knowing this lemma, knowing this fact, let's continue. Let's say one more thing about these symmetric matrices. So again, suppose A is an n by n symmetric real matrix. It is symmetric. That's still part of our assumption. Suppose I can think about A as a linear map from Rn to Rn. Suppose I have some subspace V inside Rn, a sub-vector space, such that it is A invariant. So suppose V is A invariant. What does that mean? That means for any vector V inside this vector space V, AV would still be inside this vector space V. It would not send any element of V to some element which is not in V. Then we would call this subspace A invariant, right? Now, so we have Rn, let's say this is Rn, and then we have some subspace V, say this is V. We have inner product on Rn, right? So we can define the subspace which is normal to V. Let's show it with this notation. So this subspace V perp is the set of all elements like U in Rn, such that U is normal to everything which is inside V. So the inner product of U and V is 0 for any vector V inside this subspace V. Now, the lemma is this new subspace V perp, this one, is also A invariant. If V is A invariant, the normal subspace is also A invariant. Okay, think about this one also for a few minutes, and then I would solve this one. This is also another interesting property. Again, note that I mentioned the fact that A is symmetric. We should use that property. Okay. Now let me write down the argument for this one. I'm sure a lot of you kind of can guess how this one goes. So so what should I do? I have this subspace V inside Rn, which is V is A invariant. I look at the normal subspace to V inside Rn. I want to show that this subspace is also A invariant, right? So what should I do? I should take an element inside this space. So I should take an arbitrary vector there, and I want to show, we want to show that AU is still in this subspace. But what does it mean to be this subspace? It means it should be normal to V. It means AU inner product with V should be 0 for any vector V inside the vector space V. This is what we want, right? Okay. Now, well, maybe I would go to the next page. So I want to show AU inner product with V is 0 for any vector V in the space V. Okay, how can I do that? Let's kind of choose a similar property, something similar to the previous statement. So this inner product can be written in matrix form. I can write it as multiplication of matrices. That is usually useful. That's not a bad way to do these things. So AU dot V, it can be written as V transpose AU. These two are equal, right? Because V transpose is a matrix, 1 by n matrix. A is an n by n matrix, and U is n by 1 matrix. So if we multiply all these matrices, we would end up with a 1-to-1 matrix, which we think about it as a number here, right? So I wanted to prove this statement. I want to show this is correct. Right. But on the other hand, because it is a 1 by 1 matrix, its transpose is equal to itself. So this thing here is equal to its transpose, which is equal to U transpose A transpose V transpose transpose, which is just V. Again, we use the fact that A is symmetric. A transpose is equal to A. So it is equal, the whole thing is equal to U transpose AV, right? But look at this part, AV. V is something in the vector space V, and this vector space is A invariant. So if I take any vector in this vector space and multiply that by A, I would get another vector in this vector space. So AV, let's call that V prime, again is in this vector space V. So I would rewrite this thing as U transpose V prime, which is just U inner product V prime. But that has to be 0 because V prime is in V and U is something which is normal to V. So that is 0. Note that again, we used the fact that A is symmetric. Anyway, so we showed that if we have a vector space which is A transpose, where A is symmetric, its normal complement should also be an A transpose subspace. Okay. Now let's go to the interesting thing which I had in mind when I started to take this path. The very important property about symmetric matrices over R is this one. So suppose again A is an n by n symmetric matrix over R. Now the interesting thing about A is that, as I mentioned, it's diagonalizable. So there is some P invertible matrix. More than that, I can assume it is an orthogonal matrix, actually. There exists an orthogonal matrix such that, well, orthogonal matrix, remember, is a matrix where it's invertible and its inverse is equal to its transpose. I should say that in parentheses. So there exists such matrix P such that P inverse AP is diagonal. Note that this is equal to P transpose AP because P is orthogonal, and then its transpose and its inverse are equal. Think about this one for a few minutes too, and then I would say why it's true. Try to use these things which we talked about up to this point. We can use them to prove this theorem. There are other ways to prove this theorem too, but we can also use the things I just said now to prove this one. Okay, let's start solving this one. We can do it step by step. I wouldn't solve it suddenly. We can do it with the help of each other. So the idea is to prove it by induction. Well, this is trivial for our case n equals to 1, because any 1 by 1 matrix is symmetric and any 1 by 1 matrix is diagonal by itself. There is nothing to prove there. Now, suppose we assume this is correct. Suppose, I think sometimes it's called strong induction. Suppose the statement is correct for K by K matrices whenever K is less than n. So we have that for 1 by 1 matrices, 2 by 2, up to n minus 1 by n minus 1 matrices. And our goal is we want to prove this is correct for, we want to show it for n by n matrices. We want to prove it, we want to show it is also correct for n by n matrices. Okay. Okay, let's look at the matrix A. So suppose A is such a matrix, is an n by n matrix. Let's look at the eigenvalues of A. Look at the eigenvalues of A. So let's say these are distinct eigenvalues of A, all distinct eigenvalues of A, okay? And so each eigenvalue would have some eigenvector, right? It would have some eigenvector, say U1 up to UK. I should say why I can assume this matrix has some eigenvalue. Maybe I should mention that first. I'm saying, suppose this is the list of eigenvalues of A, but do I know that this matrix definitely has some eigenvalue? Why is that true? Why can I do this assumption that there is some real eigenvalue? So I should say everything here is real. We are in the category of real numbers. Does anyone know what is the answer? Is it, so let me state my question like this. Is it possible for a symmetric matrix not to have any real eigenvalue? So maybe let me erase this one. Maybe it's a good thing to first think about then continue the problem. So we have a symmetric real matrix. And the question is that, is there a real eigenvalue? Is there a is it necessary to have a real eigenvalue or not? Or we can have a symmetric matrix which does not have any real eigenvalue. Or maybe all eigenvalues are real. What do we know about that? So if anyone knows the answer, you can say it. If you don't know that, we can think about this for a few seconds because we want to use this fact. Okay, maybe it's a good time. If you have an answer, you can just share it.
Well, since A is symmetric, we know it's diagonalizable. And
okay, that's great, but that's a little stronger. We need this to prove that, you know. At least we still have not proven that, right? We are on the direction of proving the matrix is diagonalizable. So you are certainly right. If we already know that the matrix is diagonalizable, then it would be trivial. That is true. But here we want to use this fact to prove that.
We know that any complex eigenvalues and eigenvectors come in conjugate pairs. So if we take dot product and like in the previous two things, we can swap the position of the matrix and prove that the complex part is 0.
Yeah, that is very close to what the proof is. The reason I kind of mentioned this because it is kind of related to a homework you had recently. So let me write down what the statement is and then prove it. So it's a lemma in order to prove our final theorem, which we were going towards to. So again, suppose A is an n by n real matrix, right, with real entries. And what we want to show is that all eigenvalues of A are real. So we know that any matrix does have eigenvalues because you would look at the characteristic matrix, you take the determinant, it's a polynomial, right? And any polynomial has some roots. But the only thing is that the roots might be complex, right? From the fundamental theorem of algebra, we know any polynomial over C has solutions. But here we state that those solutions, they have to be real. Now, this is kind of related to something you saw in your homework recently. So remember, when we have A, so by what I said now, we know there is some eigenvalue. We know some eigenvalue exists. So look at all the eigenvalues. So let's show them with lambda. The only point is that it might be a complex number. So the question is that, is it a real number or not, right? So by definition, this eigenvalue should come with some eigenvector. Say the corresponding eigenvector is V. So AV is equal to lambda V. Note that V is in, say, Rn is in the real vector space, not complex. So this is what we know, right? Now you did a similar technique in the homework. You could get complex conjugate of everything. So you can apply the complex conjugate on both sides of the equation, right? And AV, its complex conjugate is equal to complex conjugate of A times the complex conjugate of B. It means we are taking complex conjugate of every element in the vector or every entry in the matrix. equals to complex conjugate of lambda times complex conjugate of v. Now, the point is that a and v are real. Every element there is real, so this is equal to av. Complex conjugate of real number is itself. The only thing which might be different is lambda, because we are not sure if that is real or not, right? Now, therefore, what do we have? Therefore, lambda v is equal to lambda bar v, right? And let's see, if we take both to same side, it would means lambda minus lambda bar v is equal to 0. And assuming v is a non-zero element, it means lambda is equal to lambda bar. Therefore, it has to be a real number. So going back, yes, we know it has real eigenvalues. So let's show these eigenvalues, these distinct eigenvalues with lambda 1 up to, say, lambda k, and they are eigenvalues of some vectors u1 up to uk, and we know all of them are real, right?
Did you prove the existence of an eigenvalue?
So yeah, the point is that always any matrix has some eigenvalue, but it might be over C. Why is that? Because any matrix, how do you find the eigenvalue? You look at the characteristic polynomial, right? But any polynomial over C has some solution, right? Fundamental theorem of algebra. So any matrix, real matrix, has eigenvalue, but it might be an element of C. So that's the existent part. Now you should show that element, in this case, would be real.
But V could be a complex or a complexified vector, could it not? So then V would not equal.
No,
V.
that is not true. So when we are forming the characteristic polynomial, remember what we are doing. We were looking at a minus lambda I. If it has any solution, the determinant of that matrix would be 0. Well, let's continue here. We would go back to that because it would interrupt here. I would go back to that. So it has real eigenvalues, and some vectors come with that. So what's the point now? Well, let me think for a second about your question. Actually, the question you stated is interesting. Yeah, I think I want to address your question. So you are saying maybe the eigenvector is also complex. You are right. I think that is possible. So yes, we also should show the vector v is in Rn. This point is correct. So let's go one step further and show both of them are real. So we know AV equals lambda v, but the point you raised is that this a priori this is a complex number and v is a complex vector. We should show everything is real. That is correct. And I can apply complex conjugate to everything. And what I know is that A is a real matrix, so it means A v bar equals lambda bar v bar. That is true. Okay. So I think the proof. Okay. So the way I want to continue is very similar to what we did before. If I look at, for example, v bar, A v. Well, V bar, I should take transpose too. V bar transpose is a 1 by n matrix. A is an n by n matrix. V is an n by 1 matrix. The result would be a complex 1 by 1 matrix, which is a complex number. So we know this is a complex number, which might be real, but of course, still we don't know that. And AV is equal to lambda V. So we would have V bar transpose lambda V. And that is equal to lambda V bar transpose V. And that's just the inner product of these two vectors. Now, on the other hand, the same quantity, this V bar transpose AV, can be written as A transpose V bar, the whole thing transpose V, right? Because if I apply this transpose, I would get V bar transpose A transpose transpose, which is equal to what we had before. So these two quantities are equal. On the other hand, A transpose is equal to E. We are assuming A is symmetric. So that's what we would get. AV bar is equal to lambda bar V bar transpose, which this thing is equal to lambda bar transpose, but it's just a number. Sorry, it's just a number, V bar transpose V, and that's the inner product. And the right-hand side, they are supposed to be equal because the left-hand sides are equal. So lambda V transpose dot V is equal to lambda bar V transpose dot V. And then, so the point is that if V is non-zero, so this thing, for any complex, even a complex vector, V bar dot V is the norm of that vector, right? Just like a complex number. If you multiply any complex number by its transpose, you get its norm squared, actually. So this would be the norm of the vector squared. It would be non-zero if V is non-zero, and we would assume that the eigenvector is non-zero. Therefore, lambda is equal to lambda bar. Therefore, it is real. And if it has a real eigenvalue, it would have a real eigenvector. Okay, thank you. That was a good point, actually.
Thank you.
So going back here, we have these real distinct real eigenvalues and corresponding eigenvectors. So I can also assume this U1 up to UK dividing by their norm. I can assume they are their length is equal to 1. So I can assume length of each UI is equal to 1. Also, because of the theorem, the lemma we proved earlier, when lambda I is not equal to lambda J, UI is normal to UJ. Right. Therefore, if I look at U1 up to UK, these vectors are orthonormal in the sense that they are orthogonal and their length is 1. They are normalized. And they would span some k-dimensional subspace of Rn. So this would be a k-dimensional subspace of Rn, which is at least one-dimensional. Suppose it's k-dimensional, so for some k. So if k is equal to n, actually we are done. In that basis, the matrix is diagonal. So what if k is less than n? The point is that I can look at the normal space to V perp, and the lemma we proved is that this space is V invariant. Right. So So the point is that if I have this basis U1 up to UK, I can extend this basis to an orthonormal basis of everything, the Rn, where the rest is a basis for this V perp. So say UK plus 1 up to UN. And they construct the whole Rn. Well, because I have just 1 minute, I would just summarize the argument. The point is that in this coordinate, in this basis, the matrix A, so in this basis, the matrix A would be, well, if I look at the matrix A, it would have 4 blocks. The point is that these 2 blocks, they have to be 0. Why is that? If this block is non-zero, it means A would take something in V perp to V, which wouldn't happen. So if this was non-zero, it means A times U would have some, it wouldn't be completely inside V perp for some U in V perp. If this was non-zero, it would have meant there is some V where AV is not in V for some V in V. So when we have a vector space V, which is A invariant, and it's normal, again, is A invariant, which is the case, these 2 blocks would be 0. This block is the block corresponding to this part of the basis, U1 up to UK. And in that part, the matrix A is diagonalizable. So we would have lambda 1 up to lambda K. And the rest are 0. What about the rest? Well, if I just want to say it in one sentence, you can for sure make it a little more rigorous. The assumption of induction applies. The rest is some n by k matrix, because the rest is the restriction of the matrix to V perp, and V perp has dimension less than n. You can just diagonalize the matrix in that part. So because of the assumption of induction, we can diagonalize that part too. So we can just change this basis, we can find another basis of V perp without touching U1 to UK, such that that n by k times n by k matrix would also become diagonal. And then we would have our diagonal matrix. Okay, is there any question? Okay, if not, maybe it's a good place to stop. Thank you, everyone.